In this question, you're being asked to propose a synthesis of this specific deuterated ethanol molecule. So the important thing about this one is there's a deuterium hydrogen on this carbon with the hydroxyl group. So there's some regioselectivity there. We need to put that deuterium specifically on that carbon. All right, so we have to propose this synthesis, and we're allowed to start with ethane, this molecule here, as our only carbon source. Well, we're going to work backwards, okay? We're going to start with the product, and we're going to work our way backwards here. So let me redraw this product right here. And we're just going to take this apart and figure out what reagents can be used to make this specific alcohol with deuterium in that position. Well, in this lecture where you're finding this problem of the book, we just learned a reaction where we can add hydrogens in the form of hydride transfer reagents. We can add them to aldehydes and ketones. And we know that when we use a hydride transfer reagent like lithium aluminum hydride or sodium borohydride, when we use those reagents on aldehydes, we form primary alcohols. Well, what do we have here? We have a primary alcohol. That lets us know that we probably had the corresponding aldehyde here, which would have been this molecule here with this hydrogen on there. And what we wanted to do there was we wanted to take this aldehyde and specifically put a deuterium hydrogen on this carbon, which reduces this carbon oxygen double bond to a carbon oxygen single bond like it is here. And then we do a protonation step to put this proton on oxygen. So the way we'll make this transformation is step one, we're going to use a hydride transfer reagent, something like lithium aluminum hydride, but specifically with deuterium hydrogens on there because that's what we want to add into that carbon. Step two would be an acidic workup so that we can put that final proton on this oxygen here, right? Now, the next step is we have to figure out how we're going to make this aldehyde, keeping in mind that we have to make this from ethane. Well, how can we make aldehydes? We know we can make aldehydes from the corresponding alcohol. So I'm just going to turn this into the corresponding alcohol, which in this case is ethanol, right? How can we make that transformation? Well, we're oxidizing it. So we need to think, what are the oxidation reactions? We could do the Jones oxidation, but that makes a carboxylic acid. Remember, primary alcohols with the Jones oxidation will make a carboxylic acid. That's not what we want. We want an aldehyde here. So we have to do the PCC method here. All right. Now we have to talk about how we made this alcohol, keeping in mind that we have to get back to ethane. Well, how can we make alcohols? We know a few ways to make them, but keeping in mind we have to get back to ethane, we probably are going to do some sort of SN2 reaction using hydroxide. So something like sodium hydroxide or potassium hydroxide. We just need that hydroxide ion in there to act as our nucleophile. This carbon, where the oxygen adds, must have had a leaving group on it in order for that hydroxide to actually attack. So I'm going to just draw something like fluoroethane. Could have chose bromine, that's fine as well. And then the next step is I'm just asking myself, how can I make chloroethane? Can I make it directly from the permitted starting material, ethane? Yes, I can. I can just do that halogenation reaction with chlorine and UV light as an initiator. And this gets us back to our permitted starting material. So this would be a good synthesis of this specific alcohol with deuterium in this specific position.